So once upon a time, I threatened you with making the cylindrical coordinates business official and legit, and the time has come. So let's get into it. So let's see. So we're looking at cylindrical coordinates. Cylindrical coordinates are just a cheap ripoff of polar coordinates in the plane, but now with altitude added in. So there's our polar coordinates, and now we tack on the lamest of the lame, z equals z. So we don't do anything with that, right? So just looking, the first part right here, this is polar coordinates, and then we also add in altitude. All right, so the way that this describes a point in space, so if you have if somebody gives you the r, theta, z coordinates of a particular point, then what you want to visualize is something that looks like this. You come out by r on the x-axis, so you're out here at r, and then you swing this guy by theta counterclockwise through the xy plane until you get to whatever angle theta is supposed to subtend, and then you go up by z. So r is your distance from the axis here. It's probably, so this point here, this is our r theta z point here. So this is z, and so it's worth indicating here that r is the distance from the vertical axis, or whatever axis you're spinning this thing around here. Oh gosh, I just realized that makes it look like r is the height. Is that okay? Terrible. Here, r is this one and r is this one. There we go. Okay. And that's just in distinction from what we're going to look at in the next unit, which is spherical coordinates, which is where we're always looking at distance from the origin and only the origin. Here, r is the distance from this vertical line. Okay. So there's, when we look at Cartesian coordinates, we have the basic coordinate surfaces that you get by fixing the values of one of those coordinates, right? So if we're doing Cartesian, then let's see. So if I fix the value of x, say I say what is x equal 2? Okay, so if I'm going to sketch x equal 2, then I come out 2 on the x-axis. This is the x-axis, and then it's so x equals 2 is all points that look like 2 and then whatever, right? And so I can go in the y direction whatever I want, and I can go in the z direction whatever I want. And so in fact there's this whole little plane suspended out here intersecting the x-axis at 2, and that is the coordinate surface x equals 2. So this is the set of all points satisfying x equals 2, right? Okay, and by like token, we can do the same thing. So if we were to fix y equal 1, it's going to be going through here. Say, and then we could also have z equals 2 or something like that. Okay, so those are the usual Cartesian coordinate surfaces. So now we can do the same thing in cylindrical. And so keep in mind, right, if the object that you're setting up an integral for has these three planes, these three flat planes that I just drew as the coordinate surfaces, then setting it up in Cartesian is probably the thing that you want to do. But suppose we have like r equals 1. So let's see, so r equals 1, well, that means that you're at distance 1 from the vertical line. So in fact, any of these points on this cylinder, assuming we're at radius 1 here, are going to be, well, maybe I won't draw the dot because this is hollow. It's just the outside surface here. It's not a solid thing, right? Yeah, so there's our surface for r equals 1. And so if you're setting up a region in for like a triple integral and you're trying to figure out how to set it up, if it has surfaces that look like cylinders, then there's your hint that cylindrical coordinates are a good way to go. Or even if they're just symmetric about an axis, like an axis of rotation kind of thing. Let's see, so then if we do theta, what does it look like if I pick like theta equals, like, say, let's do pi over 3. That's sort of a nice one to draw. So that means that, let's see, so I always come out on the x-axis and then I rotate, and so if I rotated around this way to pi over 3, I'd probably be somewhere over here. And so it's anything that gets rotated that far. So it's going to be this plane right here. So anything that's, well, I didn't draw that great, but there we go. On that plane, and in fact, stuff that goes out here is also theta equals pi over 3, but for negative radius. Now, when you're setting up integrals and stuff like that, watch out for the radius being negative. It can kind of mess you up. It's not technically wrong to do so, but since people often use the formula that looks like this is a positive valued function, and so you can confuse yourself. So it's better to avoid dealing with negative radii when you can. Sometimes you can't avoid it. And then there's the surface for z equals 2 again, and it just looks exactly, it's the same thing, right? Okay, so those are the coordinate surfaces for cylindrical coordinates. So again, if you see things that look like one of these three surfaces, then probably setting up your integral in cylindrical coordinates is the way to go.